Hello everyone. Today we are going to look at curve fitting, one of the things that you see and you need a lot in engineering. Okay, for example, if you remember from our lecture on solving differential equations numerically, you remember that the function we were trying to find, we could not find analytically, and we resorted to the numerical solution, and therefore we could only find the value of the function at specific points. So if we wanted to know the value of the function at a point other than those solution points, we had to interpolate, correct? And one of the common ways to do interpolation is there any way I can fit a function to these points, and then using an approximate function, I can estimate the value at the new point. Okay, that's one of the applications, but other important applications are like, for example, you all remember the Hooke experiment probably from physics, where you wanted to measure the spring constant for a spring that you assume behaves linearly. So what you did was you basically hung from a fixture some specific weight, and here you measure the deflection in this spring due to the weight. So let's say it comes down here, and this displacement, you call it delta, and you assume that this delta is not really big, otherwise the spring is not going to behave linearly. Okay, so you let it go to static equilibrium where the spring force is equal to basically the weight, and then what you would do, you keep changing the weight and increasing the weight, and each time measure the corresponding delta, and then you plot the spring force, which is equal to the weight versus this deflection delta. And you probably end up with some points, okay, for some specific weights, specific deltas. And then now that you got these points, your goal was, well, if I want a linear relation, or if I see a linear trend between the force and the deflection, can I fit a function like this, where the spring force magnitude is equal to some constant, we call it the spring constant K, times what? Times this delta. Okay, the question is what K? Because even if I assume a line would be the closest approximation to these data points, you still have to determine the slope of that line and probably what? A y-intercept, right? So you probably have to add basically a y-intercept here, which you can call it like f naught or something. Okay, ideally it should be equal to 0, but again, the goal is, well, I can fit different lines that I think would be relatively good passing through these data points. One like this, maybe one like that, maybe one like this, correct? And so on and so forth. Of course, if I do a line like this, it's completely off from the actual measurements. But among these different slopes, which one of them I would choose, and I said that's the best fit, okay? And one of the algorithms for solving this problem is called least squares. What does that mean? Least squares means if I say this red line is the best line among all different lines, it has to provide me the least sum of squared vertical deviations. And what does that mean? It means if at any of these measurement points for their delta value, if I project those points onto this hypothetical line, so let's say I come up with these points in blue, and in each case I measure this vertical deflection. Okay, so for example, I call this, now what is it? So here, if I call this point, let's say fi and delta I, the numbers that I got from my measurement, this point here, the projection of delta on the hypothetical line, this point, I can call it f hat I, again the projection point, and the goal is, if I have n data points here, okay, so here is delta n and fn, I have n measurements. The goal is I want to find this case such that the sum I from 1 to n of fi, the actual measurement, minus the projected measurement, f hat I squared, is what? Is minimum. Okay? Can I find k and some f naught such that this summation is what? Minimum. And then those will give me what we call least squares. Now, why should we square it? Because if we don't and simply add these deviations together, well, if we define deviation as fi minus f hat I, you clearly see sometimes the point is above the line, sometimes the point is below the line. So sometimes this entity, this subtraction, is negative, sometimes positive. So if I add them, you might end up with a small number, even though these deviations could be quite big themselves. Still, some of them could be small. So in order to avoid cancellation of positive and negative numbers, we square them and then add them. And now the goal is we want to find k and what? And f naught that allow me to minimize this function. So mathematically, if we want to write it for you, basically we have to say this f naught and this k, these guys are what we call the argument for the minimum of this function. Okay, they are the argument for the minimum of this function. Now, how do we do that mathematically? I'm gonna show you right now. Okay, but that's the idea of least square curve fitting. So now, if we assume that in general we have a bunch of data points, so let's say I have a bunch of data points xi and yi, where I goes from 1 to n, and the equation of the line that I will fit between y and x is y is like a plus b times x. So b here is the same as k for us, the slope, and a is the same as f naught. And x is the same as delta, y is the same as f. So in general, if we want to mathematically formulate it, that's the goal. So this function that we are trying to minimize, if we give it some name, let's say call it s. Okay, this s is what? As I said, summation I from 1 to n of yi minus y hat I. Now, what is y hat I? As I said, it's like you put your x into the equation of this line and get what? Get the projected point. So the projected point y hat I is a plus what? B times x I, clearly, right? Because I'm plugging my x and projecting it onto this line. So I have to square this. So if I now do it, it is going to be I from 1 to n, and then yi, and I replace that, so minus a minus b times xi, the whole thing squared. Okay, now clearly, as you can see, this function s is now what? Function of a and b, right? Because it depends on a and b. So what I can do, instead of just saying s, I would say what? This is s of a and b, and now my goal is to determine a and b such that this function s has a minimum. And you know, based on your calculus knowledge, if it has a minimum and it looks like a continuous function, then the derivative of s, partial derivative of s with respect to a and b, both have to be 0. So what we'll do is we say partial derivative of s with respect to a, it is going to be equal to, now if we square it, it is going to be I from 1 to n of, this is basically we are taking derivative with respect to a, so this is the chain rule, this 2 comes out, the negative 1 comes out, so it's going to be negative 2, correct? And then yi minus a minus b xi, correct? And then this has to be 0. And similarly, the derivative of s with respect to b, which is going to be summation I from 1 to n. Now, with respect to b, you have the negative xi that comes out. So it's going to be negative 2xi times yi minus a minus bxi. This thing has to be 0. And now we try to rearrange this and come up with values for a and b. So let's expand this and see what we get. So if we try to expand this, what do we get? And then form it based on a and b. So what's the coefficient of a? If you look for a, the coefficient of a, and if we want, we can get rid of these negative 2's because it's ultimately equal to 0. So the coefficient for a is simply what? 1. And since it's a summation, so it's going to be summation of I from 1 to n of 1, correct? So it's going to be basically, and if I want these 2 negative terms of a and b, I can take them to the right-hand side. So if I take them to the right-hand side, I will get summation of 1 times ai, or a, sorry, a, not ai, 1, this goes from 1 to n, okay, so that's the coefficient of a, plus, what's the coefficient of b? Coefficient of b is summation of what? Negative xi, but I'm taking it to the other side, so it is going to be summation of xi. And on this side, on the left side, the term that stays is summation of yi. Repeat the same thing for a and b in the bottom equation. Take them to the right-hand side. Here, the constant term is summation of xi, yi. So I'll keep it here. For a, it is clearly summation of what? Xi, that is multiplied by a. And for b, it's summation of what? Xi squared. So now if you look, you have a system of equations, 2 unknowns, 2 equations, and all of these summations are simply numbers because xi's and yi's are numbers. So if I rearrange this into a matrix format, you will have summation of I from 1 to n is clearly n. So this guy is simply n, okay? We can simplify it like that. Then I have summation xi. For a, it's summation xi. And for b, it's summation of xi squared. This thing multiplied by a and b is equal to summation of yi and then summation of what? Xi, yi. All of the summations are from 1 to n. And this is enough to give me what? My a and b, because this is a known matrix called A, this is a known vector called B, and this is an unknown vector called X. So from here, clearly X is equal to A inverse times B, and that is enough to give me what? The two unknown coefficients for the line, and then B is the slope, right? So simply a summation like this is enough to give me basically the unknowns for the line. Now, before I go any further and show you what happens when it's not a line, it's a general nth order polynomial, what happens to this derivation and what happens to this formula, let's first go and show you how to do a simple MATLAB code and a simple demo, and then I show you also the built-in function in MATLAB, polyfit and polyval, if you want to see them. And then we will go about basically, as I said, higher order polynomials, and if time allows, maybe nonlinear versions. So first, let's go to MATLAB, and let's say here I have a bunch of data points and I try to fit a line to them. Now, here I'm simulating the Hooke's experiment, and so I'm making up the data. So I assume that the deflections are anywhere from, let's say, 0.1 with increment of 0.2 all the way to, let's say, 2 units. Let's make it 0.2 so that I have a known number of, fixed number of points, because I don't want to end up at 1.9, I want to end up at 2 exactly. And then y is equal to, let's say, 2 times x plus 3. Okay, or let's make it 0.3 because we assume it is, or 0.1, let's make it small, the y-intercept. Or if you want, ideally, let's say no y-intercept, so just make it 2x, but clearly it's going to be a perfect line. So here I will add some random data to it, random of basically length of x and 1. Rand command in MATLAB, as you know, generates random numbers between what? Between 0 to 1 from a uniform distribution. So before I do anything, I first plot x versus y with blue circles and make sure that these magnitudes are good, because probably it's not. My range of numbers go from 0.4 to 4, and adding a random number like 0.8, 0.9 or something big close to 1 to some number like 0.4 is just too much. So first I would like to take a look at what I have and then make some realistic data, and then the goal is, you see, first of all, it's not a set of data points as you expected, and you might say, well, what's going on here? I'll tell you what's going on. When you make this x is going to be a row vector, right? And then this rand command is going to give you a column vector, and you're adding a column vector to a row vector. That's why it is happening. So if you want to make sure you're doing it right, get rid of the different orientations for the vector. Make sure both of them are either row or column vector. Now it should be a lot nicer. And you see, for some points the deviation could be quite high. So maybe I have to bring this randomness down a little bit to make it half random. Should be a lot better. There we go. So let's say these are the numbers I got from the Hooke's experiment, right? And now my goal is to form these equations for matrix A, right-hand side vector B, and then what? It gives me the estimate for A and B. So let's do that. So what's n? N is clearly the length of vector x. So that's it. And then if I want, now I say my matrix A is what? Is n. Then I have summation of x components. So I say sum and then x. Then in the second row, I have again summation of x, and then I have summation of x squared. So first I square x using the dot power and then sum it up. Okay, so that's A, and then B vector is basically summation of y, correct? And then what? Summation of xi, yi. So I have to multiply x by y and then sum it up. Yes? So you can see it here. And now all I need is to say a solution is equal to inverse of A times B. Right? That is going to be the solution. And what do we care about? What we care about is the second coefficient in that solution. So I say here f print f, and I say the spring constant is %42f and \n, and then it is solution number 2. Okay, and that is going to be the slope of the line that I could find. So let's do it. Okay, seems like I got an error. It did not like it for some reason. Okay, and you see here I'm not editing my videos, so whatever error that comes during an operation, you can see that. Okay, I do not deliberately A and B. Okay, well, that looks fun. Inverse dot operation. It says line 11. And I do not see any. Oh, yeah, I do see something. It's a column vector. B is a column vector. Okay. So now it should work. And the slope it gives me from the interpolation is 1.91. How much was the underlying slope? 2. Okay, so you see, I could get some good approximation of the. I will never get perfect because my data were not perfectly on the line. It's impossible. Now, the smaller you make this, of course, you're going to get better what? The smaller you make the randomness, right? Uncertainty in measurements, measurement noise, and anything like that, you will get a better approximation, right? So let's make this randomness smaller. So they are almost on a line. And now, you see, there we go. I got way better numbers, of course, because my sensor noise is, and my experiment accuracy is high. But let's say here we got with 1.91 or whatever. Now on the top of this initial plot, I would like to also plot for you the fitted line so that you can see what's going on. So that is the plot of original data. Now I say hold on, and now I want to plot for you x, but this time I want to show you the approximate function, which is solution number 1, or if you solution number 1, which is the y-intercept, plus solution number 2, which is the slope, times what? Times x, and I will use red data and I connect them with a line, and then to make it professional, I would also add x and y label, and I will add a title. And there we go. Okay, clearly you see this line. And to make it even better, I always suggest use a legend. and say this is experiment data, and then the fitted line or fitted curve. Okay, so legend is always making it better. There we go. And if the legend is on the way and it is occluding a portion of your data, I also suggest you say location and then say best. Let MATLAB get it out of the way and put it in the best place. There we go. Okay, so you clearly can see what is happening in this experiment and in this curve fitting. Okay, very clear, very nice. And now there is a command in MATLAB which basically does the exact same thing as what we did here, these 4 lines, and the command is called polyfit. Okay, it is called polyfit. So instead of all of this, all you need to pass to this command is basically, so you call it, you say polyfit, and you pass to it the x data, the y data, and n. N is the order of the polynomial you are trying to fit. Okay, so you can use it for more than simple line. You can use it for any order of polynomial. And a line is order 1, so you say order 1. What does it give you in return? It gives you a vector p, which includes the coefficients of the fitted polynomial, basically. And then the important thing is this p. Okay, what order does it give you back? You have to pay attention to it. So if you go and look at the syntax and how this guy works, okay, the way it is working is it considers the first coefficient to be the highest order. Unlike me that said a plus bx, what this one does is bx plus a. So if you wanted the slope here, that is solution number 1. The first entry of p is the slope, not the last entry. You see, last time I said solution number 2. If this time I want to talk about p, I have to say what? I have to say that is basically p number 1. Okay, so here I do it this time with the polyfit instead. Now here, of course, it is going to be picking on me because it says what is solution. So instead of this, I can say this is going to be p number 2 plus p number 1 times x. And that should do the same thing for me. You see, it's the same thing. And now here, it's interesting. It does not give me the same number. Remember last time we found because if you look at p, gives you a small number and then a number for p. But if you look at my number, okay, so here, let me comment this out. And comment this out, and this one, let's say I don't want to plot, just interested in the number. If you look at my algorithm, it says 194, MATLAB says 1.02. So it seems like MATLAB is not perfectly doing this, and it is probably doing a little bit of what? A little bit of change. Now, why? If you go and look here, it says MATLAB polyfit centers x at 0 and scale it to have a unit standard deviation. So MATLAB first change your x data to something like x minus x bar divided by the standard deviation of x, then fits the polynomial to it, okay? This way it is avoiding the shift bias and the scale bias. Okay, so it has a little bit more than this simple application of this 2 matrices and inverting it. First, it modifies data x, fits the data to it, and then it undo that transformation of the variable to give you the slope and everything. That's why the number MATLAB gives you is a little bit different than mine and a little bit more accurate, actually, right? 2.02 was closer to 2 than 1.91. Okay, so if you want later in a separate video or so, we'll talk about this, what we call normalization of data, center it at 0 and making it have a standard deviation of 1 instead of arbitrary, because your data clearly has not an average of 0. Clearly you see the average is 1.01, and the standard deviation of our data is also not 1, is 0.6055. So what it does, it creates something called x bar, and then x bar is going to be x minus mean of x, and the whole thing is a single number, so I don't need dot division, std of x. So it makes this x bar, clearly some data are now negative, and now if you look at the mean of x bar, it is almost 0. And if you look at the STD of this data, it is 1. Okay, so it fits now a transform version of x and y first, and then undo it. It makes the calculation of the slope and y-intercept more accurate. Okay, so just telling you what's going on behind the scene. Okay, so this is called polyfit that MATLAB does. And also, another thing is this. So let's say this is the polyfit that you did in MATLAB, and now you want to plot the data. If you want to plot the data, you don't need to manually, because let's say if your polynomial is higher order, it has an order of 10, then you have 11 of these, and then you have to type everything here, right? P number 11 plus P number 10 times X plus P number 10 times X squared, all the way to P11 times X to the 10. And it's going to be a big expression. So MATLAB has another built-in command called polyval. And polyval, given vector P and the data X, will give you what? This Y bar here. So this is your Y bar, right? You can say Y bar for me is this much, and here you say plot for me what? X versus Y bar, right? But again, instead of this, what you can say is the command called polyval, and all you need to pass to polyval are what? The coefficient P that you just found using polyfit, and then your X data. And that will give you that basically replacement of p-values into the original polynomial function, calculating the projected points, and this is going to give you the projected points so you can plot the fitted line. Okay, so we learned here about two other functions in MATLAB that we use a lot, polyval and polyfit. Okay, now with all that in mind, I can show you that if in general you have a bunch of X and Y data points, and this time instead of fitting a line, you want to fit an nth order polynomial in general to them. So you still have your data xi and yi, with I being between 1 to n, and your goal is to fit a polynomial of order m. Let's say n and m are not the same. Okay, and so the goal is this: you want to fit a function like y equals, and here we try to go with a notation. So we say something like a naught plus a1 times x plus a2 times x squared plus all the way to a to the m times x to the power m. So you are fitting a polynomial of power m, order m, to this, and here remember that n is typically way bigger than m. Otherwise, it's not really a curve fitting problem. It is just going to be an exact solution. And that's another topic that hopefully in another future video I'll talk about it. When you try to fit a polynomial to a bunch of data, the problem that could arise is you take this order of polynomial too high that your polynomial will pass through each and every one of points. So let's say here in this example, in this previous experiment, I had a what? I had x, and x was how many data points? 10, correct? Now, can I choose a polynomial of order 9, which has 10 coefficients in it, to fit that data? Well, sure. Then what you will end up for those equations is going to be 10 by 10. 10 unknowns and what? 10 equations. So this time, this function that you will plot is not going to be a fit. It's going to pass through each and every one of these points. It's a higher order. It has a lot of oscillations in it, and it is completely capable of passing through every point. And you say, well, what's wrong about that? Why can't I do it? In this hook experiment, I have 10 data points. Why can't I pass a polynomial of order 9? Well, fine. But what happens if you have more data points? That's the problem of overfitting. So let me explain it a little bit. I guess I have to explain it, then I come back. It's important. So if you have, as I said, a bunch of data points where they are kind of behaving linearly, let's say here I have 6 data points, and instead of fitting a line of best fit to them, you will pass a what? A 5th order polynomial with 6 coefficients. So your polynomial is now going to be like this. Okay, so here the order of the polynomial is 5. For this one, it is 1. Then you might say, well, this 5 looks better to me than the 1, isn't it? Because it's not approximately passing through points, it's passing through all of them perfectly. What's wrong? The problem is coming when you try to approximate a point between them and do some interpolation. For example, you want at this x, which is between these 2 points, you want to know the value of your function, or maybe this x, okay, or somewhere in the range between them, anywhere, as long as it's not at exact points. Here, doesn't matter. And what you will do is you project this point onto these functions. One of them will give you this, one of them will give you this. Now, which one do I use? Well, here the deviation might not be too much visible. But when the order of this polynomial gets bigger and bigger, these oscillations are going to be wilder. Okay, what do I mean by that? I mean something like this. Let me show you. So in this case, I'm not exaggerating it because m is 5, but when this gets bigger, it goes through this point, but instead of going a smooth transition to the next point, now you have something like this. And then this, and then this, and this, and this. So you're going to get bigger oscillations. So now, instead of your blue curve giving you that point, now your blue curve will give you this point, which is completely off from the rest of the experiment. So you see, this function that is passing through each and every one of points, because the order of it is too high, then it is capable of giving you very, very bad interpolations or extrapolations for data in between your measurements. And this problem is what we refer in the literature to overfitting. Okay, this overfitting is a big problem. So typically this order of the polynomial is quite less than the number of data points, a lot less in most of the experiments when you have a lot of measurements. okay? Because you might say, well, if I repeat this experiment next time, instead of 6 data point, I have 10 data point. Are you going to change the order of polynomial from 5 to 9 for me? Well, then it seems like the underlying function depends on how many data you are choosing instead of what is actually happening between the dependent and independent variable. So we have to be very careful about this overfitting. And then you might say, well, how do I know which order is right? Well, you either have some knowledge, like the hook experiments. You know, for the hook experiment, the force of the spring versus deflection acts a little bit linearly as long as this delta is what? Small. And when delta is getting big, then again, based on previous knowledge, you know the function is going to go cubic. Okay, so you're never going to fit a 10th order polynomial to the hook experiment. So you either have some prior knowledge from, let's say in this experiment, solid mechanics and behavior of material in the elastic or plastic region, or what you do is you keep increasing the data, the order of the polynomial, until the interpolation error is going to be really bad. And for that, what you will do is you are not going to use all of your data points for the interpolation. So what do I mean by that? Let's say here you have lots of data. So here, let's say I have 11 data points, right? Or 12 data points. Let's make it 13, 14, and 15. So I have 15 data points, and although the trend looks quite linear to me, instead of order 1, I can go all the way to what? To an order 14 or 15 that passes through each and every one of them with those all big wide oscillations. So what I will do, I will chop this data into at least 2 parts. One of them we use for interpolation. Some of the data I will keep and not use in their interpolation. So let's say I will spare this data. I'll keep it for later. I will keep this data, and I'll try to make sure those data that I call test data, I choose over all of the range. I'm not going to just choose in a specific at the end, at the beginning, or middle of the range some data. So randomly pick some data from all over this range. And let's say for this data, these data points, I will later check whether the function that you pass through the rest of them, which we call training data, whether this function that you're passing is going to give you a big interpolation error for these test points or a small one. So if I pass a line through them, right? If I pass a line through them, then at the x point for the test data, you have what? The line predicts your point to be here, 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 and what? Here. And you see these deviations of the test points from the projected points of the line, these are not big. But again, if instead of line, I say, well, what? I have how many data points? This is 3, 4, 5, 6, 7, 8, 9, 10. So I will pass a 9th order polynomial to this. And that is going to give me some big time oscillations. And now, instead of me projecting using the red, I will project using the blue. And here, actually, you have to do an extrapolation, but that's fine. So here, the projection using the blue is going to be here, right? Here, 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 and here. And clearly you see now the deviations between the points that we kept for testing, the test points, and the projections from the blue points are now what? Getting bigger and bigger. So what we plot is some of these projected errors, right? some of the projection errors for test points, and this is based on the order of that polynomial. And you probably will see until some specific value this error comes down, and then after that it starts going up, and you say, well, this order probably here is my optimum order. Okay, so in many training algorithms, including this curve fitting, neural networks, and many others, they always try to find a good order beyond which you're witnessing the increase in this projection errors. Okay, so again, you divide the data into two parts. Most of the time we do something like 70%, 30%. 70% of the data we use for finding the slope or the coefficients of this polynomial in general. We call it training data. And then uniformly, we keep some data, about 30% of the data off. We do not use it for curve fitting. We call it testing data, so we can use them for calculating this projection error. And then based on this, we try to find an optimum value for the order of the polynomial to be using. But again, keep in mind that the order we are using is typically less, or sometimes better say, way less than the number of data points. Now, if that happens, then we can show that the equation to find these coefficients a0 to am will be, again, in matrix format. If I want to write it in matrix format, it will be something like this. This is going to be a big matrix A. Then you have the unknown vector of these coefficients, where here you have a0, a1, ... to am, and here you have the right hand side of known values. Now, what goes here? Here is going to be n, the number of data points, just like the previous case. Then we have what? Summation of xi, if you remember, right? So we had summation of xi. And then if you see here in the bottom row, the order of the power of xi's is increasing. So it's xi squared. If I have one more element, it would be xi cubed. Here is xi to the 0. Here is xi to the 1. So the next xi is going to be xi to the 2, correct? So the power is increasing. And how far do you go? Well, remember, this is an m by 1. This is an m by m. And this is an m by 1. So what you need to go is m rows and m. Actually, it's m plus 1. Excuse me, it's m plus 1 because you go from 0 to m. So it is m plus 1 times m plus 1. And then this is m plus 1 times 1, and the same thing here, m plus 1 times 1. So here, this is element 1, element 2, element 3, right? So if m was 2, you go to 3 elements, and that's it, correct? So listen again. If m was 2, how do I find this last one? Here you're extrapolating, basically. Yeah, I can show you the derivations, but we don't need to go there. So if m was 2, right, or last time m was 1, you only went to power 1. M is 2, you go to power 2. M is m, of course, you go to what? Power m. Now, the next one, start from the second element of this. So it is going to be some xi, then it's going to be some xi squared, some xi cubed, ... Now here is going to be what? Some xi to the m plus 1. and then you keep going. Here, what would you have? Again, if m was 1, you end up with power 1. So now this element should start with power m already. And then what? Keep going up each time by 1 power until you get to what? If you see the difference in power, it's m. So this is going to be what? xi to the 2m, or m plus m. Okay, so this is that matrix. And here, the first one was sum yi, the next one was sum x to the I, y, x to the 1 yi. So if it goes down, the last one will be sum xi to the m times yi. Okay, and here, if you call again this whole thing matrix A, this is called unknown vector x, and this is called known vector b. Again, inverse of A times B will give you what? All of these unknown coefficients. So this is the formulation for an M order polynomial. Okay, in general, you can use this, you can code it, and you can do least squares curve fitting for a higher order polynomial. The command polyfit that I showed you in MATLAB will do that for you. Okay, now one last topic we have to talk about, and that is nonlinear curve fitting. Now it has a lot of depth to it, and I'm not going to go over all different methods of nonlinear curve fitting. So the one I will show you are the one that you can convert back into linear curve fitting. And what do I mean by linear and nonlinear? So if you look at here, the function, when I try to find these coefficients, if I look at these equations that I have to find the unknown coefficients, in terms of these unknown coefficients, a and b, my equations are what? Linear, because I'm multiplying a bunch of numbers to a and b, and it's equal to what? A bunch of other numbers. So you don't see a to the power 2, b to the power 2, log of a, sine of b, or any nonlinear functions of these unknown coefficients. So that's why we call this what? We call this linear curve fitting. Because in terms of the unknown coefficients, the equations that you will derive are linear. Now, many times that's not the case. The function that you try to find in terms of y as a function of x, if you do it, you end up with nonlinear set of equations based on a and b. And you might wonder, like, where, when? So sometimes, let me show you, you have some measurements, and you know that, based on your physical knowledge, you know that y as a function of x is what? It's a logarithmic function or exponential function, okay? So let's say it is an exponential function. So you get the data here, you get the data there, you get the data there, you get the data there, another data there. And you know this should be what? A decaying exponential like this. So basically it is implying that y should be some initial value a times b to times exponential of negative bx. Okay, so here you clearly can see, if I write my equations in terms of these unknowns, so I have 5 data points and 2 unknown equations. If I write them, I will get what? I will get y1 equals a times e to the negative bx1. So this is the first equation that I will get. Now, is this equation in terms of a and b, is that linear? No. For a, it could be, but not for b, because b itself is not directly showing up. Instead, what? Exponential of negative b is showing up in the equation. And then I have what? y2 to be a times exponential of negative bx2, and all the way to here, let's say y5. Okay, y5 is similarly a e to the negative b times x5. And now the question is, find a and b such that if I form that summation, S was summation of basically I from 1 to 5 of yi minus the function evaluated at the xi, which is a times exponential negative bxi. Okay, so this thing here, this guy here is your y hat I. This I want to be minimum. Okay, clearly again, you see in terms of b, your equations are not linear. And so even if you take derivatives and set the derivative of s with respect to a and b, definitely that equation will also not be linear, and you cannot simply solve it by what? By its matrix notation. So then you have to solve nonlinear algebraic equations and several of them, which is harder than doing a linear set of equations. So what would you do? First, you try, before you try to attack this problem, you try to see if you can linearize the function itself in terms of a and b. Linearize it again in terms of a and b, not y in terms of x. The relation between x and y has linear components of a and b in it. Can you do that? So then you can do linear curve fitting. So again, let me tell you one more time here. If you take partial derivative of s with respect to b here, in this case, with respect to b, or a, doesn't matter, even if you do it with respect to a, look what happens. So here, coefficient of a is this guy here with a negative, so it is going to be summation of negative 2, correct? And then e to the negative bxi, right? Times yi minus a exponential negative bxi. This has to be 0. Clearly, you see that in terms of a and b, this equation is nonlinear. And again, in terms of b, if you do it, it's going to be summation of, now for b, it's negative xi, correct? That comes out times the exponential itself. And then you have also a negative a and a 2, correct? So if we do it, it's going to be negative 2a, and then times negative xi exponential of negative bxi times the function. And again, clearly you see in terms of a and b are getting nonlinear equations, which are harder to solve. So what is the goal here? Is to linearize the function. Where would you see stuff like this? A lot. For example, if you have what? If you have a capacitor or an RC circuit, correct? As you know, if you have an RC circuit and you are trying to discharge the capacitor, so here you have a resistor, here you have a capacitor, and here, let's say you have a key that you can open and close. So this is R, this is C, this is voltage in, and you can also measure the voltage out across the capacitor. So clearly you know, if you connect the key where this capacitor is charged, the V out equation, it is going to be like initial number, whatever it is, times exponential of negative t to the RC. Okay, and here, let's say this initial voltage you can measure, but you don't know the value of R or C, so you basically use your chronometer, measure the time, measure the voltage at several time points, and then plot them versus each other. So Y is the voltage out and X is the time. And your goal is to find what? This coefficient RC, which in this case is 1 over B. Okay? Or let's say you know R, you want to find C. So there are lots of things that you see in nature that have that type of behavior. The relation between Y and X in terms of the parameters, unknown parameters, is nonlinear. So what do we do? As I said, if I have this equation Y equal A exponential negative BX, can I linearize it? Well, not always, but sometimes you can. In this case, what you need to do is take a natural log of both sides. And if you do it, you know that natural log of two numbers together is natural log of first one plus natural log of second one. And natural log and exponential are inverse functions, so they cancel each other. So from here, you will get natural log of y is equal to natural log a plus that negative b comes out, so it's going to be negative b times x. Now, if you look, if I call the natural log of a new parameter, let me call it c. Now, and this natural log of y is simply a number because yi's are all what? They're all numbers and xi's are numbers. Okay? So here, my coefficients will be it's going to be like a line. I'm fitting a line, but not between x and y, between natural log of y and x. And then what? The line that I'm fitting, it has a coefficient c and it has a coefficient negative b. So in this case, I can say that my equations for finding these two unknowns will be something like this. So I have to replace the previous yi's I had with this guy. My x is still the same. A is this constant, b is this constant. So it is going to be c and negative b. And remember, c itself is natural log of a. So if you want, you can directly say what? Natural log of a. And here, this is going to be n, whatever the number of data is. And then here is summation of xi, no difference. This is summation of xi, and this is summation of xi squared. But this time, your y is natural log y. So it's going to be summation of natural log of yi. And here is going to be summation of xi times natural log of yi. And guess what? This is a matrix of numbers. This is a vector of numbers. It will give you what? A and B. So if you can linearize your function in terms of the parameters that are unknown, it makes life a lot easier, and you can easily use what? This linear curve fitting methods. If you cannot do it, then you have to resort to other methods which are beyond the scope of this video. So I will stop the video at the moment, and thank you so much for your attention.